Alright guys, I'm so glad everyone was as excited about this as I was, where we're going to try to start taking our notes at home so you're not scrambling in class, trying to keep up with where I am, and ultimately falling behind, missing the actual, content that we're trying to talk about here. So we're going to introduce Unit 3 in this new way. Hopefully it works out. Really hope it does. So electrostatics. So electro, of course, relating to electricity. Static, you should know, means not moving. So we're going to talk about charges, charged particles that are not moving. So first page in your notes talks about just kind of an introduction to what we're going to be looking at in this. So we're going to start off with kind of the guy who got the ball rolling, Democritus, which I found this little gem. Oh goodness. Look at Democritus. Ladies, I don't know if he is single, but I can tell you that he is very dead. So I'm sorry to have to break that news to you. So this guy Democritus, he was a Greek philosopher. So pretty much all of our great ideas seem to come from the Greek. He was the first one that said that anything, any object, is made up of some kind of smaller pieces, which at the time he thought they couldn't be any smaller. He thought as small as it got was the atom. So Democritus says atoms are the smallest thing, and everything in the world is made up of those. We know now, of course, that he was wrong. Not entirely, though, only half wrong. So the things that we know are atoms today are made up of three different pieces. So he's right that these things were made up of smaller pieces, but even those smaller pieces have some smaller pieces. So what makes up a proton? Or, sorry, what makes up an atom? Well, like I just said, protons. We also have neutrons, and we have electrons. So out of those three, protons and neutrons relatively similar in size, but the electron is actually much smaller than the other two. So because of some kind of electronic force, some kind of interaction that we're going to look at between these particles, electrons orbit the nucleus of the atom, which is made up of protons and neutrons. So if we want to look at that, we're going to look at a helium atom. So this is kind of Democritus's idea. He thought an atom was the smallest thing, but we know now it's made up of a few smaller pieces. So the electrons, they're the ones that orbit. They're the yellow guys out here. So yellow electrons. And then the nucleus, which is made up of the protons and neutrons, is right there in the middle. So protons being the red and neutrons being the green. So you can see in the red and yellow there are signs. So that tells us that protons and electrons carry an electric charge. So the plus and the minus are used to represent that electric charge, and that's what causes them to be attracted to each other. So in most atoms, you're going to have the same number of protons as you do electrons. So we'll say that in most atoms, there are as many electrons as protons, and the opposite charges that these two have kind of balance each other out. So even though it's made up of things with positive and negative charges, they balance out so there's no overall charge. All right, so we've been throwing around the word charge a whole lot. At least I'm not saying arbitrary, right? So what is it? Actually, we're still not sure what charge is. It's really difficult, if not impossible, to even say what it is. For all that we need to know in this class, it's just some kind of property that some object has. So it's like mass. You know, what is a mass? It's just something that there is. So charge is just something that some things have, and it's represented by the variable q, lowercase q. Remember, big Q we had for heat. So the simplest way to think about charge is just to say that opposites attract, something that you've probably been saying since before you were even able to come to school. Things have. Protons just have a charge, and just by convention we call it positive. As the guy in the Khan Academy said, that is just totally arbitrary. We could have called it anything we wanted, but someone chose positive. So electrons are positive and protons are positive and electrons are going to carry a negative charge. So more important, they're just opposite of each other. So 3 simple rules to remember. I'm sure you already are aware of these 2. Anytime you have 2 positive charges, they are going to repel one another. Anytime you have 2 negative charges, they're going to repel. The only time that you can get an attractive force between 2 charged objects is when you have opposite charges. So a positive charge and a negative charge will attract one another. The amount of positive charge that one proton carries is actually equal to the amount of negative charge that an electron carries. So even though they're different sizes, they have different masses, they still have the same amount of charge. So keep in mind that's just magnitude. When we get into working with it, we'll call the signs a little bit different. So like I said before, most atoms have the same number of protons and electrons, so overall there's no net charge. So what we're going to focus on are cases when electrons break free from the atom. So the atom overall has a positive charge, and that electron is taking its negative charge to something else to give it an overall negative charge. So when we talk about charge, the unit that we'll use for that, the SI unit for charge, is the coulomb. Coulomb. And it's shortened just by capital C. And the smallest unit of charge that anything can have, there's no unit of charge smaller. The smallest you can get is the amount of charge that a proton or an electron has. So we call that the fundamental charge. And that's represented by the lowercase e. The fundamental charge is just the amount, oh my goodness, it's just the amount of charge on a proton or electron. So then the actual amount there, like you saw in the Khan Academy video, E, there we go. The actual charge a proton or neutron has is just about 1.6 times 10 to the minus 19 coulombs. So positive when it's for a proton. If we're talking about an electron, then we just make E negative. So far in physics, whether you took one or college prep last year, you learned a lot of conservation laws. So conservation of mass says mass can't be created or destroyed. Conservation of energy. Energy can't be created or destroyed. We use those arguments in our fluids unit about conservation of energy. We did the same thing in the thermal physics unit. So now we're going to introduce a new one, conservation of charge. All it says is that charge can't be created nor destroyed. So we can't make charge, we can't destroy charge. All we can do is transfer it. So charge can be transferred between particles. So it has to be transferred in such a way that the amount that one loses, the amount of charge something loses, is equal to the amount of charge something gains. So if one thing loses electrons, something else has to gain them. Those negative charges can't just disappear. So two examples of that, of charge being transferred from one thing to another. If we take a rubber rod and rub it with a piece of wool, then what's going to happen is the rod is going to pull electrons from the wool. The rod will pull electrons from the wool. So overall, the rod, it lost electrons, it lost its negative charges, so the rod is going to have a positive charge overall. And if the rod lost, nope, nope, that's not right, and I can't rewind, so I'm sorry about that. So the rod pulled the electrons from the wool, so the rod is going to have a negative charge. It pulled those extra electrons, which means the wool, having lost some electrons, is going to have an overall positive charge. So, kind of unlikely but entirely possible that you may run into questions that ask about this specific situation between the interaction of rubber and wool. Kind of the opposite thing happens in the example with glass and silk. So in the first example up here, the rod pulled electrons from the wool. But if we use glass and silk, then the silk cloth is actually going to pull electrons from the glass. So since the silk cloth is pulling in extra electrons, it's going to get an overall negative charge. And since the glass lost electrons, it's going to get a positive charge. So the last thing we want to talk about in charge is how can we measure it? How can we actually determine whether something does or does not have a charge? And the device that we can use for that is called the electroscope. So electroscope is a device that we commonly use to demonstrate how charge works. So you have some kind of metal bulb connected to a rod, connected to two thin leaves. So let's jump down to this little space down here and start working on it. Alright, so let's add in this picture of the electroscope. Alright, so here is the metal bulb that we were talking about. And it's connected with some conductive material to these two metal leaves down at the bottom. So this is the evacuated glass chamber. Just looks like a big glass ball. So if we have some negatively charged object that gets brought close, so keep in mind we don't want to touch, it's just going to be brought close to that metal bulb that's on top, then all these electrons are going to take all the electrons in the metal bulb at the top and push them away. So they get pushed down that metal rod into the two leaves. That's as far away as they can get. So these electrons here want to get away from these ones. So with the electrons pushed away, that just leaves a bunch of extra positive charges up at the top. So the bulb at the top takes on an overall positive charge. The two leaves, both having a negative charge, start to repel each other. So they push apart. So if we flipped it around, if we had a positively charged object approaching the bulb, then the opposite would happen. We'd be left with a bunch of negatives here. All the positives would be down here in the leaves. Since they still have the same charge, they would still push away from each other. So that is about all we need to know for charge. Okay, so I was just about to wrap this up and realized that's actually not true. I do have one more thing I want to say, and that is how can we figure out mathematically the overall charge that an object is going to have. So remember that we called the overall charge Q. So Q is going to be equal to, well, what does charge come from? It comes from something either having too many or not enough electrons. So it's going to depend on the number n of electrons that you either gain or have lost. So some number of electrons times the charge that each one has. So E, our fundamental charge. If you wanted to calculate the overall charge Q, well, that's just because of some number of fundamental charges. If you wanted to figure out what number of electrons you have, well, that would just be the total charge divided by each individual charge. That's the total number that you have.